EBSCOR, the experimental program to stimulate competitive research, is a National Science Foundation grant program. The goal of EBSCOR is to strengthen science and engineering research and education throughout the United States, and to enable states like Wyoming to be nationally competitive in these areas. EBSCOR aims to improve scientific infrastructure in Wyoming and build science, technology, engineering, and math research capacity across the state. One way Wyoming EBSCOR helps strengthen science research and education is through student programs such as the Summer Research Apprentice Program, also known as SRAP. SRAP is an intensive 6-week paid research experience for high school sophomores, juniors, and seniors aiming to attend college. It offers students a hands-on research opportunity in science labs across the University of Wyoming campus. Students work one-on-one with a faculty mentor throughout their time in the program. SRAP not only provides students with a paid internship and real research experience, but also helps prepare them for college life.
So first, we will be presenting Mr. Troung Cai from West Covina, California. He will be presenting production of three-dimensional scholastic-based microfluidic systems for fluorinated oil droplets formation.
Hi, my name is Harvey, and my research is about production of three-dimensional elastic microfluidic system for coordinated oil droplet formation. So in a nutshell, it's developing a new technique for generating droplets. So I work with Dr. John Oki and Andrew Hansen for this project. So for an overview, I'm going to talk about what is microfluidic and how is it going to be applicable to the work. So droplet microfluidic is a system of channel that manipulate fluid, and it has to be smaller than 100 microns. And the main goal of droplet microfluidic is to create picoliter size droplet, so very tiny droplets. And so currently we have like 3 techniques that create a droplet right now. The first one is T-junction. T-junction because it looks like a T. The next one is called flowing. You have 2 streams of liquid flowing together, and then at some point they break off. And the last one is flow focusing, when you have a big channel and then a small channel and a big channel again. So all of these 3 techniques is very nice, but they have one limitation. That's the only 2D technique. Because the droplet that we want is perfectly spherical. And a sphere is a 3D structure, and a 2D device couldn't make a 3D structure very well. So that's why we want a 3D device. So so we try and make a new method, and also we want to have multiple generators per device. So why do we want these droplets in the first place? When we have there's like 3 big applications for microfluidics. The first one is cell sorting and cell fusion, phenotype screening. So this is the picture of cell sorting. What you would do with the droplet is that you're gonna surround the cell with the droplet, and then you can actually give the electric charge to the cell, and then you can separate them using a magnet. So that you can, because doing this, you would be able to be like more organized with your cells And that's very useful for a biological system when everything is a chaos. So also you can do something called cell fusion, which you surrounding two cells. One of them going to be stem cell, the other one going to be a regular cell, let's say a liver cell. And when fuse them together, the stem cell will eventually develop into a full organ, like in this case the liver, so you can do organ transplant. The last one is phenotype screening. This is used for drug discovery. We have, like, let's say a bacteria that generate insulin, but we want to know what kind of DNA, what kind of protein that actually involved in the process. So you can actually encapsulate the bacteria inside the droplet, and then put kind of like a fluorescent thing, and then you can screen it and know what kind of protein is involved in the process of making, in this case, insulin. So how do I fabricate my device? I use the technique called soft lithography. First, I'm going to have a silicon wafer, which is like a thin sheet of silicon, and then I'm going to put photoresist, which is a chemical, on top of it. And then I'll put a transparency mask, which is like a piece of transparency which have a pattern that we design on it. And then I will expose that under the UV light for a day, and then that pattern will be incorporated into the wafer. And then I can put something on top of it called PDMS, which is a chemical, and I then put it inside the oven for like an hour or maybe two. Then it will solidify, and we can detach it from this wafer. And what we would have is that a piece of solid PDMS that has channel on it, which is the pattern that we designed. So this is how the device would look from the top view. That is the top layer, that's the bottom layer, and that's the thin film in between them. For the top layer first, I make these two holes in the middle, and then I bond the thin film on top of it using something called a plasma cleaner. And then I poke another hole in the film, and then I create another hole at the edge. And then I bond the bottom layer horizontally. And what I would get is the device that looks like this. We have top, bottom, and then the thin film in between, and the top going this way and the bottom going this way. So what do we buy? For water, first we kind of generate water droplet, and what we found is very, very pleasant because the droplet is very small, so that's really what we want. And so we go into generating oil droplet. So what you can see right here is that oil droplet is much bigger than the water droplet because the attraction of the oil has a very high attraction for the PDMS that we use. And as you can see, it's very hard for the oil to move. That's why I have more time to get bigger. So because of that it suggests that we should have something called a breakup inducer, which I'm going to talk later. And also, because what happened to the water droplet, we found that we can actually have multiple generators per device. Because the device have like this way and this way, so you technically can make unlimited amount of hole between them. So that can have theoretically unlimited amount of generator per device. So what the inducer I was talking about is called a step system. It has a big channel, a small channel, and then a big channel again. So when the big oil droplet squeezing through the small channel and going back to the big one, break the big droplet into smaller droplet. And also we're gonna start testing multiple generators per device so that we can generate droplet more efficient. And this is my reference. And I would like to especially thank for the National Science Foundation and Wyoming ESCOR for funding my research, and the SRAP for providing me this opportunity, as well as Dr. John Oki and Andrew Hansen and the rest of the team in the Contact Fluids Lab for helping me throughout this process. Any questions? Any questions or comments? Please.
What was your biggest challenge in doing such an intense project in such a short time?
Oh, my biggest challenge is actually because when we first started this project, we don't really know how the oil would act inside such a big channel, and also because we have a 3D structure, so we don't know how it's actually floating up, floating up in the structure. So we actually have to do trial and error a lot on that, so that took a lot of time. Any more questions? Please.
Because I listened to your presentation, makes me curious, what do you plan on studying?
I'm planning on studying chemical engineering and biomedical engineering.